Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogba Jr., your math tutor. I am an instructor of mathematics at the University of Liberia. In today's lesson, we want to look at finding or proving the derivative of natural logarithmic function. So how do we find the proof of the derivative of a natural logarithmic function? That's exactly what we want to do in this lesson. And in next lesson, we'll look at the proof of the derivative of the general logarithmic functions, whether the base is 10 or the base is 2, the base is 3, and so forth. Remember, whenever we talk about natural logarithmic function, we mean ln of x. And this ln of x means log of base e of x. So whenever the base is e, then we have a natural logarithmic function. When the base is any other expression other than e, then it is under the general logarithmic function. When it is 10, it's a common logarithmic function because we commonly use base 10. So let's prove the derivative of the natural logarithmic function. So consider f of x to be equal to ln of x. So if f of x is equal to ln of x, and then we actually use the first principle of derivative, now we can also use the implicit differentiation method. That is, we know that y equals to ln of x, but this ln of x can be rewritten as log of base e of x. Rewriting this into exponential form, we have e raised to the power y is equal to x. So, but since we have now reached to finding the derivative of exponential functions, so we are not going to touch this for now until we get to finding the derivative of exponential functions. So f of x is equal to the ln of x. So we know that from the first principle of derivative, we have a formula that states that f prime of x is equal to the limit of f of x plus h minus f of x divided by h, as h is approaching 0. So we already know that f of x is equal to the ln of x. So all we need is f of x plus h. So that is, since x now has been replaced with x plus h, we just need to replace x here with x plus h. So it's ln of x plus h. So now we have f prime of x equal to the limit. So this expression now is ln of x plus h. And then this is just ln of x all over h, as h is approaching 0. Now what do we know? Whenever we have the limit of one function minus the limit of another function, we can bring in a property that states that ln of a minus ln of b is equal to ln of a over b. So this is our a and this is our b. So we can rewrite it as the limit. Now we'll factor out this h, 1 over h. So this now becomes ln of x plus h divided by x. But because we need 1 here, all of what we're doing here, we are aiming at deriving this standard limit so that we replace this standard limit with some e. So because we need 1 in the first term, we can rewrite this x plus h over x by saying x over x plus h over x. This h is approaching 0. So we have f prime of x now to be the limit. Now we can also bring in this property. R ln of a is equal to ln of a raised to the power r. So it means this r can move to this power. So this 1 over h represents r. So we can send it right here. So we have the ln of 1 plus h over x raised to the power 1 over h as h approaches 0. . Now we also observe that from this particular standard limit, we have 1 plus x over h. Here is 1 plus h over x. Now, x here is representing a in that x is equal to a, and then h is equal to x, right? So, if you have x over a, you see that the power is like the reciprocal of x over a, which is a over x. So it means we must also have this reciprocal as this power. So what can we do? We just need to rationalize x so that we can bring this x right here and we will have x over h. That's just all. So we have f prime of x now to be equal to the limit. So we can factor out this ln. So bring the ln behind the limit. We have the limit of 1 plus h over x raised to the power x over h. And then what is left? We have 1 over x. That's exactly what is left, h approaching 0. So we have f prime of x now equals to the limit of 1 plus h over x raised to the power x over h. As h approaches 0, this whole thing is just equals to e. So we just have this to be our e. But this is expressed to the power 1 over x. So it's 1 over x. So what can we do? This 1 over x, we can send it behind the limit, the ln. So it's 1 over x ln of e. But we told you initially, okay, so we did not put it here. So we know that ln of e is just equal to 1. Why? Because ln of e means log of base e of e. So when the base and the argument are the same, it's just equal to 1. So now this would give us 1 over x times 1, which would just be 1 over x. So in general, the derivative of ln of x is just 1 over x. Again, the derivative of 1 over x is just 1 over x. But we are considering a case wherein we have a linear function, just x. A linear function x raised to the first power and a coefficient 1. What if it was not a linear function? What if it was a quadratic function, a cubic function, a radical function, or what if this coefficient was not just 1? Maybe it was 3, 4, 5, and so forth. So we can find a general form for this. So we say if we have f of x to be equal to f of x is equal to the ln of some ax in general, you could just write it as x. But I'm using this e to represent the coefficient of this x. F prime of x will be 1 all over ax times the derivative of ax, d bar dx of ax. So there's a general form. Now let's look at just 1 or 2 examples. In the following lesson, we will solve more problems, some challenging problems under this topic. But let's look at a few examples, just 1 or 2. Example 1. If we have the function f of x is equals to ln of 5x, for example, how can we find its derivative? We look at this. We have f prime of x is equal to 1 all over whatsoever that is within here. You rewrite it 1 all over 5x. Then you say times the derivative of this 5x. So we differentiate this 5x. So f prime of x now will just give us the derivative of 5x is just equals to 5. So it's 5 all over 5x. So when 5 and 5 cancel, we just have 1 over x. So it means the derivative of ln of 5x is just equals to 1 over x. What if we had the function f of x equals For instance, we have the ln of x squared minus 1. So again, f prime of x should just be equal to 1 all over what is here? X squared minus 1 times the derivative of what is within. So the derivative of x squared is just 2x. The derivative of a constant, this number is 0. So finally, this will give us 2x all over x squared minus 1. So this is how the proof of, this is how we actually prove, the derivative of the natural logarithm function. And these are few applications of them. So in the next lesson, we will solve more problems on how we can deal with natural logarithmic functions. So thanks ever so much for watching, and I'll see you in the next lecture. Please don't forget to subscribe. Don't forget to like. Don't forget to share. This tutorial is not sponsored by anyone, but rather I alone. So if there's any means that you want to sponsor this tutorial, it's up to you. You are welcome, most welcome. Just inbox me or just leave at least a comment in our comment section and I'll hit you up. Thanks so much and see you in our next lesson.